Hi, so let's come to the question number 2. The question number 2 is that we have a known trajectory and we want to calculate the axial force at different location of the drill string when the drill string is pulling out. So here's the givens. So we have a trajectory with true vertical depth of 8,000 feet with build and hold configuration. Our OD of the outside diameter of the drill pipe is 5 inch. The buoyancy weight of the drill pipe is 20.15 pound per foot. The kickoff point is at 1,000 feet and our horizontal departure is 8,000 feet. The build rate is 1 degree per 100 feet, and when the tripping out initiated, our weight on bit is assumed to be 0, and the frictional coefficient is 0.2. So what we want to calculate is the axial force when tripping out at top of the drill string, which is on the surface, and also at the beginning of the build section, and at the end of the build section, and also how much torque we need to rotate the string in the hold section. So we just calculate the torque we need to rotate it to overcome the friction in hold section. Okay, so we also need to assume that the low tension condition in the build section. So because when you studied that parts, and you will find out there's like different assumptions with different solutions. So you use the one that's suitable for your situation. So in our situation, we assume the build section is in low tension. Okay, so let's get started. So first, we just draw the configuration of the wellbore. So we have a kickoff point at 1,000 feet with a build section and hold. So our horizontal departure is 8,000 feet. Our true vertical depth is 8,000 feet also. And we have a build rate of 1 degree per 100 feet. So this R1, this is both R1. And we have an angle here, theta. And we have another angle here, this theta 2, this theta 1. Okay. And from the build rate, we can easily calculate R1 equals to the 180 over pi times 1 over Q. So you just follow the steps, you get the R1 equals to 5,829.6 feet. Okay, and as we showed in previous quiz classes, we can easily prove that theta 1 equals to theta 2. So we just use theta here. And then for this geometry, we can, because we want to calculate the axial force at this section, and this point, and this point. So what we need to do is we have to know how long is the whole section and what's the angle of it. So based on the given of true vertical depth and horizontal departure, we can formulate these two equations. First is the length of the whole section times cosine theta plus R1 times the sine theta. So which we get two lengths here and here. So these lengths add together equals to the kickoff point, the true vertical depth minus kickoff point, which equals to this one, right? It's like obviously the true statement. And this is our equation A. And the equation 2 is we have a hold, the length of hold times sine theta equals to this line here. I put a triangle. And plus R1 times 1 minus cosine theta, which means we have R1 is like this, right? We minus R1 times cosine theta this section, so we basically get this section, right? So this section plus this section together equals to the horizontal departure, 8,000 feet, right? So here is our equation B. So we have two equations with two unknowns. The first unknown is the length of the whole section. The second unknown is the theta. So if you have fancy calculator, you just plug those numbers in, then you get the solution, right? So if I'll show a step that if you don't have those fancy calculator, how do you derive this equation and solve for the theta and the L hold? Okay, so let's get started. So first, we just plug all the known number in to get this equation as less symbol as possible. So just with only unknown here. So we have L hold times cosine theta plus 29.6 times sine theta equals to 7,000, and L hold times sine theta plus 5728.6 minus 5728.6 cosine theta, which I expanded this one here, and equals to 8,000, right? So now we can just put two expressions of L hold by using the theta, the sine theta or cosine theta, either of them, both of them actually. So from the first one, you just move the cosine theta from this side to the other side, and the second one is the same thing, but you just need to move this one on the other side. Then you get these two expression of the L hold. If our previous statement is true, then L hold and L hold are the same, then we can just simply equal these two equations. Now we can get 1 equals to 2. We have a single equation with only one unknown is the theta, but in two different forms, sine theta and cosine theta, right? So now, if you have fancy calculator, you can just do the calculation and make sure you get theta from 0 to 90, right? You don't want to get like the angle is too big because it's periodically, I mean, the sine theta can have multiple solutions. So here, if you can solve it, you can solve it for theta. If you can't, I'm doing the down-based way. Just use the pen and hand and paper. So now we need to expand this, right? Expand to multiply each term by sine theta and multiply each term by cosine theta. Then you get 7,000 sine theta minus the R1 sine theta squared equals to 2270.4 cosine theta plus the R1 cosine theta squared, right? Because we know that cosine theta squared plus sine theta squared equals to 1, right? We can either move this one on the other side and move this one on this side to eliminate this second order term. Then we get this expression: 7,000 sine theta minus 2270.4 cosine theta equals to 5729.6, right? Because we have these two the same, then just lift it up outside this one and make it inside equals to 1. So we get this expression. So here we need to recall the identities of the trigonometric. So because we know that sine A minus B equals to sine A cosine B minus cosine A sine B, right? And we can make angle B here by divide both sides by square root of 7,000 square plus 2270.4 square. This is like a pretty common trick if you want to make sine or cosine out of two numbers. So now we can have the cosine beta equals to this one, 7,000 divided by this combined term, square root, and sine beta equals to 2270.4 and divided by this one, right? You can verify this. It's definitely less than 1, and also we can verify that this is also true for these two sine and cosine we just made. Right. Then we can just calculate this too. Yeah, actually I proved it here. So cosine beta equals to 0.951 and sine beta is 0.308. And the sum of square of both terms will be equal to 1. And now if you're interested, you can just prove it by yourself. And now we just use this, and we can use either of them to get the angle B. Angle B will be 0.314 rays, which equals to 17.97 degree. Right, now we know the B, and we have single sine cosine function. So now sine A minus B will equals to this one, because we divided both sides by this square root of 7,000 square plus 2270.4 square. Right, you divide it this side and divide it by this side. So this one, and you combine them, you get this one, right? So this one on the left hand side, the right hand side will becomes 5722.6 divided by this, and this equals to 0.7786. Right, if you get this, and you can easily just use inverse sine function, you get A minus B equals to 51.13 degree. And now with knowing B equals to 17.97, we can know A equals to 69.1 degree. Right, and our L hold with either of these functions shown here, you can easily plug the number in to get the L hold will equal to 4617.9 feet. So this is the more complete procedure to solve the system equation with sine and cosine by hand. Right, so you can skip this one if your calculator can do the job. Right? But it's good to know that you can solve it. Okay, so now if we know that length, then we can easily calculate the first one, because when the tripod initiate, the tripod is just put the drill pipe out of the well bore. So when tripod happened, it's easier to we have weight on bit equals 0, so it's easier to calculate from the bit to the surface. So now we just first consider the end of build section, which is also the start of hold section, right? So we can draw a free body diagram, and we have a drill string here, which has gravity applied on the mat. So our drill string is like this, right? And we have, when we pull this one upward along the wellbore, we have axial force, and we have friction in opposite direction. Okay, so this is sliding frictional. So we know that how to calculate, right? It's actually just the one that's perpendicular to the plate times the friction factor, right? So which is here, and we know this angle is theta, and actually with this triangle, this angle is theta, right? If we know that the weight is the gravitational force, which is the weight per length times the length, and you times the sine theta, right? You get this one. This is times theta. You get this one. And times the frictional factor, you get this frictional force. And then the gravitational force will have another force acting on the axle, which is also just the weight per length times the length which is this one, right? The gravitational force, and times the cosine theta, which is the another force is acting like this. So it's the same direction as the frictional force. So add them together, you get this one, because this has to be balanced, right? Because we're putting it in a constant speed, or like in a stable condition. It's not accelerating. You're not accelerating the tripping out. So which means that this force equals to this force plus this force XL, right? You just plug the number in, you get you get the answer. The F1 will equals to, so this is F1, 5580.39 pound. Okay, so that's our question C, to get the axial force at the end of build section. And now we